Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 22nd lecture in the series, and today we are continuing the topic which we started last 2-3 lectures back. It's a linear prediction analysis of speech. So, in the last class we are discussing about the capsule analysis of speech. So, basically the need for capsule analysis of speech is that, so using a capsule analysis we can able to split the components of vocal tract and the excitation components of a speech signal separately, so that we can extract the features from each of these components separately, and we can use them for performing various speech tasks individually and then in a combination also. So that way in the capsule analysis we can able to separate the vocal tract and the excitation source components. So, if you look at here in this, so this is a normal the representation of a speech as a by viewing the speech production system as a linear system. So, if you excite the vocal tract system with the excitation, then the output will be a speech signal, and now the speech signal is related to this excitation and the vocal tract system response in a convolution manner in a time domain, whereas in a frequency domain they are multiplicative, like E of omega, V of omega corresponds to the spectral information corresponds to the excitation signal and the vocal tract system. And so, since they are product, so we can get the spectrum that is associated to the acoustic signal of a speech. If you want to have the spectral properties separately for excitation component and the vocal tract component, one way is that if you take the log magnitude of the spectrum, where if you take a logarithm on this spectrum where the excitation component and the vocal tract component can be separable, that means they become additive, right, and from that if you ignore this phase component, then the leftover will be, you have a log magnitude spectrum of a speech can be addition of the addition of log magnitude of the excitation spectrum and the log magnitude of the vocal tract spectrum. So, here in analytically you can able to see these two are additive, but even if you perform this perform the log magnitude spectrum, you do not see this addition, you can able to separate it over here, but instead if you take the inverse Fourier transform on this log magnitude spectrum, you can able to see the signal will be something like this. You can get the inverse Fourier transform of the log magnitude spectrum. You can able to see the outcome, or you can say that the capsule output or the capsule signal appears to be like this. In this, the initial coefficients of the spectrum are more of provides the vocal tract information, and the later part provides the represents the excitation component of the speech signal and all. So, that way from this, if you look at the initial portion of the capsule, this is basically points to or characterizes the vocal tract system, and this characterizes the excitation component, and this you can able to observe from the capsule domain, these the components of the capsule from initial part and the later part. If you apply again the Fourier transform, right, you can able to see the vocal tract, the spectral envelope of the vocal tract, and the spectrum corresponds to the excitation signal, which is a ripple, and the spectrum contains the flat spectrum, which is the characteristic of the excitation for a periodic case, right. And a similar thing, this is for a voiced segment. In case of unvoiced segment, the excitation is a noisy signal. So, therefore, you do not see the periodic the peaks with a periodic separation that you do not observe in the capsule signal and all. So, this is the capsule signal or the capsule for an unvoiced speech segment, and this will be the capsule for a voiced speech segment and all. So, we can able to see that this is the log magnitude spectrum, and in the log magnitude spectrum, if you look at here, So, the ripples are superimposed over the spectral envelope of the gross spectral envelope, and here the gross spectral envelope can be characterized to, or is more of related to the vocal tract shape, the shape of the vocal tract in production of the particular sound, and these ripples are nothing but are the characteristic of the excitation signal, because the excitation signal is a periodic signal. So, therefore, the periodicity is observed as the harmonics in the spectral domain. So, therefore, the ripple component on this in this signal corresponds to the excitation, and the broader, or you can say the gross envelope, corresponds to the vocal tract system and all. So, this we observed from the capsule analysis, and so now with this background, now we will try to see how to extract the capsule features from the LP analysis. So, we observed that with the help of LP analysis, so the vocal tract system is represented by a set of prediction coefficients, or the weighting factors that are known to be linear prediction coefficients. So, these linear prediction coefficients, they more or less approximate the vocal tract system, but the linear prediction coefficients are very sensitive, If there is any small perturbation, then the roots of the filter, so they may be shifted from like inside the unit circle to they move to the outside the unit circle and all. So, the moment the roots, if they shifted from inside the unit circle to outside the unit circle, then the system becomes unstable, that is not the desirable one. So, the linear prediction coefficients, if you directly use as the feature vectors for performing various speech tasks, so we end up with a problem, because if there is any small disturbance or small perturbations, because there are after all coefficients like with the floating point coefficients, and then in the approximation based in the quantization, if you have a small changes that are added or that are used that are there in the part of the approximation or quantization, then that leads to the system may become unstable. So, that is not, so therefore, the LP coefficients, since they are very sensitive, so you cannot use directly the LP coefficients for performing various speech tasks. Instead, as I mentioned that, so in a capsule domain, the whatever the linear prediction coefficients are there, so if you can perform the capsule analysis on it, and then if you derive the capsule features from the LP analysis, after the LP analysis, then whatever the coefficients you will get, or whatever the samples you will get in a capsule domain, and those can be viewed as the linear prediction capsule coefficients. And whereas, as I mentioned, that the capsule coefficients are more stable compared to the linear prediction coefficients. So, therefore, we can use the capsule coefficient derived from the linear prediction analysis of a speech, known to be linear prediction capsule coefficients, and they can be used for performing various speech tasks, like for example, in case of speech recognition, for discriminating the sound units, you can use the linear prediction capsule coefficients, and similarly in case of speaker verification or speaker recognition also, you can use the linear prediction capsule coefficients, and so on, like discrimination of languages, discrimination of emotions, and so on, right. And for performing the linear prediction, to derive the linear prediction capsule coefficients, we have to follow certain sequence of steps or certain sequence of operations. The first thing that will perform here will be the pre-emphasize the speech signal, because if you look at a normal speech signal, particularly the voice speech segment, you can able to see that the spectrum will be something like this. Here the spectrum is plotted as a log magnitude spectrum, and you can able to see that there are three formats are present, and the first format or the low frequency components are very dominant, highly dominant, because if you look at the format height, or you can say that the energy that is associated to the first format versus the second and third formats, they are very much different. That means almost like if you look at the third format is almost like a 30 dB or 40 dB below that of the the energy that is associated with the first format. That means what I want to convey here is that the frequencies around the first format are very dominant, or almost like the order of magnitudes like 10 power 3 or 10 power 4 times higher than the energy that is bared by the frequency components around formant 3, formant 4 and so on. So, here the important thing is that it is not that the real magnitude that is present at the formants are not important. The thing is that the formant locations are important, that is nothing but the frequencies that are associated around the formants. So, those are important. But here if you perform a normal analysis, since there is a lot of dominance of the low frequency components, so the formants, extraction of formants or determining the formants, higher formants will be difficult. We cannot accurately estimate the high formant frequencies in the midst of the dominance of the low formants or the low frequency components. So, therefore, the idea here is that if you can able to perform, if you can pre-emphasize the signal, it means that, so if you can able to like somehow enhance the high frequency components, so that my spectrum will be, this is the actual spectrum of a speech, and then if you perform certain like modification or some enhancement of the high frequency components, my spectrum observed to be like this. It means that the high frequency components are enhanced, so that the high frequency components also get are almost like they are also with the same energy as that of the low frequency content. Now, you can able to see the formant frequencies like this. So, from this you can able to estimate the low frequency as well as the high frequency formants also you can able to estimate very accurately. For that what we need to do is that we need to perform the pre-emphasis. We need to pass the speech signal through a pre-emphasized filter, so that the response of a pre-emphasized filter will be something like this, right. If you look at here, at low frequencies they are not amplified, that means this is the dB, like they are not amplified, the low frequency content is not amplified, but as slowly if you look at the frequency response of a filter, at high frequencies you can see the frequency components will be enhanced by almost like a 30 dB. So, therefore, earlier in the normal spectrum the high frequency components are like they if you look at the signal energy at the high frequency component, they are almost like a 30 dB lower compared to the first format, right. And now with this the pre-emphasis, the high frequency components will be enhanced. So, with that my spectrum looks like this, and now with this you can able to estimate or determine, compute the formats more accurately. So, for that this we use this kind of a filter response, and this filter response you can able to obtain by using this it is a simple first order FIR filter, So, if you look at the transfer function of the filter, it is simply like first order 1 minus a into z power minus 1, and this a is varying from 0.9 to 1. So, if you, this is in the z domain, and then if you look at its corresponding time domain relation, if you take inverse Fourier transform, you can h of z is nothing but, right, h of z is nothing but my s of z by e of z, right. So, if you do that, then with that if you can able to see, you will get the corresponding, the relation in the time domain is nothing but this is the pre-emphasized signal s hat of n, and this is nothing but 1 minus a z of a z whole power minus 1. This is nothing but just taking the difference between the signal signal samples, that means s of n is nothing but nth sample, s of n minus 1 is nothing but the n minus 1, that is a previous sample. It is a scaled by a, and where a in a normal most of the practical filters and emphasis filters, a will be close to 0.95, is about 0.95, right. So, if you take the approximation, if you take instead of 0.95, if you take a 1, then the pre-emphasis is nothing but, given a speech signal, if you take a successive difference, if you take a successive sample difference of a signal, it becomes it is nothing but the signal is pre-emphasized, this is approximation, right, the signal is more or less is a pre-emphasized. So, that way the first step need to be performed will be all the formats to be like particularly higher formats to be enhanced, so that you can able to estimate these format frequencies accurately later on. So, that is the goal objective of this particular process, the pre-emphasis process and all. So, for any of the speech task, to extract the features from a speech signal, the first thing that need to be performed is that we need to perform the pre-emphasize pre-emphasis, right. So, we will pre-emphasize the speech signal, so that the all formats will come will be reached to the same level of power, signal power, so that we can able to extract the formats with appropriate techniques more accurately. So, this is the first step that is involved, known to be pre-emphasis, right. So, the next one will be frame blocking or framing the speech signal, because this we come across. Suppose if you have a speech signal, speech utterance corresponds to a particular sentence. So, the length of the speech signal will be around 2 seconds, 3 seconds, or it may be 5 seconds, right. So, if you want to perform the LP analysis, as we have already mentioned, because the speech utterance is a time varying one, because the speech utterance contains the words, where the words contains the different sound units. So, therefore, each sound unit has a specific characteristics as per the vocal tract configuration and other excitation signals. So, therefore, we cannot perform the LP analysis on the whole speech signal, right, on the whole speech utterance. So, instead we need to perform the LP analysis on a a segment of a speech where you can able to observe a stable characteristics or a steady characteristics, right. So, therefore, we have observed that in a speech segment. So, if you choose the duration of a speech segment like around 20 to 50 milliseconds, more or less the characteristics of a speech segment will be same or almost like similar, because that 20 to 30 milliseconds, that is because of our the physical characteristics of our speech production system, because in the articulators that are involved in the speech production, they cannot move beyond that speed, right. This after all, it is a physical system. The movement of a tongue and the movement of the jaw and other articulator movements, they are limited. They are limited in speed. The movement are restricted or constrained. So, the movements cannot move with very higher rates. So, therefore, you can able to observe that if you analyze the speech segment or within like a 20 to 50 milliseconds, almost the characteristics will be stable. The characteristics will be the stable or steady characteristics are observed. So, based on that observation, the speech utterance will be splitted into frames, of duration like around 20 milliseconds or 25 or 30 milliseconds, around that, right. So, therefore, for doing that, what we need to do, we will will split the speech signal with a duration of 20 milliseconds or 30 milliseconds. You can say that suppose frame 1 starting from here, and then this is suppose assuming that the duration is suppose 30 milliseconds. So, it will be up to this point. Then the frame 2, we are not starting from this. So, we are starting from just slightly shift from the frame 1's or the initial position or starting position, the frame 2 will be started. So, it will be it takes its 30 milliseconds duration, then the frame 2 will ends over here. Similarly, the frame 3 will be started after some shift with from the frame 2, right. Similarly, frame 4 will start after some shift with the frame 3, right. So, because if you look at the frame 1, frame 2, frame 3, frame 4, so they are shifted by almost like the same amount, and then you can able to see the overlap across the frames. That means, frame 1 and frame 2, if you look at, there is a overlap of almost this one, almost like a 2/3 of a frame or like a 3/4 of the frame is overlap. That means, the 75% of the frame 1 is shared with the frame 2. Similarly, the frame 2, the 75% of the frame 2 is shared with frame 3. So, that way you can have an overlap, because this overlap is required when you estimate the LP coefficients or any features from this speech signal. So, they should be correlated. There will be a correlation can be observed. Otherwise, no, if you take the non-overlapped signal, the coefficients that are observed in the frame 1 and the coefficients that are observed in the frame 2, they are not much correlated. So, to provide the correlation between the smoother feature vectors or feature coefficients from these frames, adjacent frames. So, we need to have these frames should be overlapped. So, suppose for example, if you have a 20 milliseconds frame and suppose to provide 75% overlap, so the frame shift will be 5 milliseconds. It means that for every 5 milliseconds you have a frame, you have a speech frame. So, that way we will segment the speech into frames with the overlapped frames, right. So that way you can see the frame blocking is nothing but split the speech signal into frames, and the duration of the frames will be like vary from 20 to 50 milliseconds, right, and we will provide some overlapping. That overlapping again, that depends either 60% or 2/3 or like a 3/4, that depends. So that way we will the next step will be we will provide the we will split the speech signal into frames with the overlapped frames, so that the correlation between the LP spectral coefficients will be smoother, right. Then the next thing is that when you are doing the frames, when you are performing the framing, you can see that at that means at the boundaries of the frames where the sudden truncation will be done. That means here we are splitting here, that means here the like you can say that the transition here are like when you are splitting the signal using a frame, here there is sudden transition is observed. The sudden transition is observed because you are cutting here. So therefore whatever the signal amplitude, if you from that like if you see the next one, there is a sudden shift, a sudden change will be there. So therefore to avoid these sudden transitions, because if you do this way, like this is nothing but rectangular window, right, you are splitting the speech signal using a rectangular window. So with that what happens is that at the boundaries, right, you can able to see a sudden truncation. So this sudden truncation leads to distortion in the spectral domain. This leads to a distortion, like you have seen that the side lobe leakage that you observed because of this rectangular window. So to overcome this sudden transition, we can in the next step what we are doing is that we will impose these sudden transitions are smoothed out, smoothened by imposing imposing the window on these frames. So the window will be smoothed out. You can see that in the window, at the middle of the window there is won't be any attenuation at all, and then as you progress from center to the ends, there will be attenuation. That means the signal will be multiplied with this window. So therefore the signal will be slowly tapered off. The signal will be slowly tapered off. So because of this slowly tapering offered by this window, so the side lobe leakage will be less. Side lobe leakage will be less. But at the same time, since you are tapering that, so in the time domain here the signal, the sample amplitudes will be distorted. So to overcome that, again, since we are doing the overlapping here, like when you perform overlap and addition, so whatever here the samples that are attenuated, so they will be taken care by the next window properly. So that way you can overcome that those issues related to the attenuation of the sample amplitudes at the ends. So here we are in general we use this window will be Hamming window, and this is the expression for a Hamming window. This is an expression for Hamming window. You can able to see that when n equals to at the extremes, you can it offers almost like very close to 0, and at the middle when n equals to like n by 2, it offers the higher value. It offers a higher value, right. So that way the third step will be after framing to overcome these the sudden transitions, we need to taper the signal. So therefore taper the edges. So for tapering the edges, we use the Hamming window to taper the edges approximately. So next thing will be, so after that we have a speech frame, and then if you we need to estimate the prediction coefficients, LPCs. So we know that we already gone through that. So from a speech frame, for estimating the LP coefficients corresponds to that particular speech frame, we need to perform the analysis. So for that what we need to do? So we need to solve this expression, right. We need to compute the autocorrelation coefficients, right, the P autocorrelation coefficients, and then we need to that means we need to perform to derive the LP coefficients. So first of all we need to perform the autocorrelation analysis on the frame, and we need to estimate the autocorrelation coefficients from 0 to P. That means the P plus 1 autocorrelation coefficients has to be computed, because these are required for estimation of LP coefficients, because the LP coefficients what we are doing after you compute autocorrelation, after you perform autocorrelation analysis and compute the autocorrelation coefficients, then we have a relation, right, AK summation of AK into R of I minus K equals to R of K, right. We have that equation, and with that you will have some set of P equations are there. If you solve those P equations, then you can get the optimized LP coefficients, because that we have derived from the error analysis, right. So, you compute the mean squared error, and then if you take a first order derivative with respect to each of the prediction coefficients and equate to 0, you will get a set of normal equations, and if you solve the normal equations, you will get the LP coefficients. And in that normal equations, we have observed that that normal equations you can able to approximate, or you can able to represent by using these autocorrelation coefficients, that we have seen. We observed that in the last class and last before class also. So, once you have the LP coefficients are available at the process, so these LP coefficients you can able to estimate using the Durbin's recursion. So, this Durbin's recursion is nothing but we know that when you represent this in a matrix format. So, we have seen that the matrix that is observed is the Toeplitz matrix. So, it is that means with respect to principal diagonal, you can able to see the upper diagonal elements and lower diagonal elements, they are same, they are symmetry. So, then one can able to exploit the symmetry using this recursion proposed by Durbin. So, with the Durbin's recursion you can able to estimate the LP coefficients. So, in the process of estimating the LP coefficients, we can also get the other coefficients or other types of features known to be reflection coefficients, log area coefficients, log area ratio coefficient, and from these LP coefficients you can also derive the capsule coefficients, right. So, we know that how to derive the capsule coefficients, right. So, we have seen in the last class and even today also we summarized that how to perform the capsule analysis on a signal, right. So, with that in the similar way you can also compute the from the LPCs, because the LPCs gives you the LP spectrum, and then from the LPCs you can able to get the linear prediction capsule coefficients, right, in the same process whatever we have mentioned, right. And the same process if you look at here, again here also you can get some kind of recursion. So, with the recursion expressions you can able to derive the linear prediction capsule coefficients from the LPCs directly. And as I mentioned that in the linear prediction capsule coefficients, when you observe, the number of coefficients will be very huge, but the first initial coefficients corresponds to the vocal tract response or the vocal tract characteristics. So, here in this case in general in LP analysis, the number of coefficients that can be considered from the 0th coefficient will be, it is like for example 1.5 times the P, where P is the order of the linear prediction analysis. So, the P may be, as I mentioned that as we have discussed, it varies from 8 to 15, where the 10 or 12 will be the reasonably good approximates of the linear prediction order P, right. So, therefore, the P will be like 10 to 15, and so therefore, with respect to that, suppose if you choose 8 is the order for example, then the 12 or 13 coefficients are the reasonably good number of representation of the capsule coefficient for a particular frame. So, that way we can able to estimate the linear prediction capsule coefficients for every frame, and that acts like a feature vector for performing various speech tasks, can be used for either speech recognition, speaker recognition, speaker verification and so on. So, now we got the linear prediction capsule coefficients, but the derived linear prediction capsule coefficients are observed to be, when you perform the analysis and all, it is observed that in a linear prediction capsule coefficients, right, the lower order capsule coefficients are very sensitive to spectral envelope. Spectral envelope means, as we have seen the low in the formant frequencies, the first formant will be very much dominating, right, compared to second and third, right. So, with that the spectral slope, right, so that dictates the dominance of the first formant with respect to the other formant, and this spectral slope will be like this is variable, or this is that depends upon the speaker. So, when you from speaker to speaker, even though if you utter the same word or the same sentence or the same sound, you can able to see the spectral slope will be very different. The spectral slope will be different. That means the energies that are associated to various formats, they differ. So, with that the spectral slope will be differing. So, and with that variation of the spectral slope, so you have ambiguity in discriminating the sounds. You have ambiguity because for the particular sound it is uttered by speaker 1 and speaker 2 and speaker 3. where even though the formats are similar, where because of the difference in the spectral slopes, so the estimation of formats will leads to error, and then with that you can, that leads to even the erroneous detection of particular sounds also. So, what I want to convey here is that in the outcome of capsule coefficients, they are somewhat sensitive. That means, the lower order capsule coefficients are sensitive to the spectral slope, right. It means that even though the formats are same, if the spectral slope is different, then the coefficients are different, because that is not the requirement, that is not our objective, because the spectral slope may vary, but the formant frequencies remain same. When you say R, right, when you say R, the formant frequencies for the different speakers, they are more or less similar, but as the spectral slope is changing, and here the capsule coefficients, the magnitude or the capsule coefficient values will change, and that is not the desired one, right. Suppose for the same utterance R, like uttered by different speakers, more or less the capsule coefficients should remain same, right, but you observe the difference because of the difference in the speakers or because of the other things, right. And similarly, the higher order capsule coefficients, they are very much sensitive to noise. That means, for example, you uttered the sound unit R, for example, in a quiet room where there is no noise at all, right, and same thing, that means if you the same person, when you utter the R in the open space, for example, where there is a wind blow is there, or in a room where a fan noise or fan is rotating, that gives you some noise kind of a thing. So, under that, if you record the vowel R versus the vowel R that is recorded in a very clean or like a noise free environment, where you is supposed to be like as a human you can perceive the same R, but when you try to recognize that by a machine, and because here the capsule coefficients they vary, because in the presence of fan noise, if you capture the signal R from a speaker, then along with this acoustic signal, the fan noise also will be added to that. So, that is a noise, and because of noise the capsule coefficient, the higher order capsule coefficients will vary, right. And with that, you can see when you try to find out the distance between the reference versus this one, you can able to see a change, and that leads to the classification errors and all. So, what I want to convey here is that the capsule coefficients, whatever is obtained, they are sensitive. That means, the lower order capsule coefficients are sensitive to the speaker characteristics and other things, right, whereas the higher order capsule coefficients they are sensitive to noise like environment, but it is supposed to be robust, they should not be sensitive, right. So, to avoid that, when you are performing the capsule coefficients, when you derive the capsule, after deriving capsule coefficients, to make these lower order and higher order coefficients to be insensitive, right. So, therefore, what we do is that we will pass or we will provide a weighting to this capsule coefficient, because as I mentioned, the number of capsule coefficients for a frame will be 3 by 2 times p, where p is nothing but the linear prediction order, right. Suppose, for example, if we choose the p equals to 10, so the number of coefficients will be 15, right. Out of 15, the first initial coefficients, initial 3 or 4 coefficients, they are very much sensitive to the spectral envelope, like or the speaker characteristics or some other one, and the last coefficients, the last 4 or 5 coefficients, they are very much sensitive to noise, to the high frequency noise, high frequencies, right. So, to avoid that, to make them to be robust or insensitive to the spectral slope changes or the noise, so what we do is that we do the weighting. So, it means that what we do is that in the capsule coefficients, so the middle coefficients will be enhanced, right, and whereas the coefficients at the edges, that is nothing but the coefficients, the lower order coefficients and the higher order coefficients, so they will be given a less weight compared to the middle coefficients, because these coefficients are sensitive. So, therefore, we do not consider or we do not give much importance to the capsule coefficients at the lower side and capsule coefficients at the higher side, right. So, that way for doing that, what we can do is that we will pass the capsule signal through a band pass filter in the capsule domain. So, where the band pass filter will offer a characteristic something like this. So, it means that the lower order coefficients and the higher order coefficients compared to this, the central coefficients are the coefficients in the middle portion. So, they will be emphasized, they will be given more weight, or they will be given more weight in performing the various speech tasks and all. So, for that we use the window in the capsule domain will be of this type 1 plus q by 2 sine of pi m by q, where m is varying from 1 to q, like the number of capsule coefficients, like if it is whatever 25 or whatever and all, like 15 or 20 something like that. So, that offers you at the middle, it offers the higher value, it is almost like 1 plus q by 2, where q is for example 15. So, 1 plus 7 by 7.5, that is 8.59 times will be given at here, and whereas at the edges it gives you a weight of 1. So, that way it is known to be parameter weighting or known to be capsule weighting. So, if you apply the capsule weighting on the capsule coefficients, then they are known to be weighted capsule coefficients or known to be weighted linear prediction capsule coefficients. Normal linear prediction capsule coefficients are derived by the, you have a linear, we have the linear prediction spectrum, on that we will perform a capsule analysis and you will get a linear prediction capsule coefficients. But the linear prediction capsule coefficients are sensitive, that means the lower order coefficients are sensitive to like speaker characteristics and speaker specific characteristics and other things, like, and higher order capsule coefficients are sensitive to noise like environment. So, we had to overcome this. So, for that we had to weight the linear prediction capsule coefficients with appropriate filter, with appropriate window known to be this way of this type. So, the outcome of this weighting process known to be weighted linear prediction capsule coefficients. The next thing is that the capsule coefficients what we have derived, so they represent the spectral envelope or they represent the basically the spectral properties of a particular frame. That means, we are taking a frame of 20 milliseconds or 30 milliseconds, then we are performing LP analysis and all, we will get a capsule coefficient, and those capsule coefficients basically represents the, like we are taking initial coefficient, they represent the vocal tract. So, therefore, the capsule coefficients of a frame, they basically represents the spectral envelope of that particular frame. It means that the capsule representation will effectively represent the local spectral envelope, that means the spectral envelope at that particular instance or at that particular frame, right. So, if you use these capsule coefficients as it is, then you can able to see that from frame to frame, that means there will be a kind of, you will get only the local information, that means for that particular frame how the, what will be the shape of the vocal tract and spectral characteristics, you can come to know that. But if you want to analyze, if you want to, like for example with respect to speech sounds, because when you utter the ah, it is not that ah is corresponds to only one frame. So, that ah, if you try to analyze, the duration of the ah will be around like 150 to 200 milliseconds, right. So, in this duration we have several frames, we have about 20 frames or 30 frames will be there, right. And if you want to, and another thing for the production of ah, it is not that the characteristics are steady, that means for production of ah from beginning to the end, it takes the different shapes of the vocal tract. At the beginning the vocal tract may be in a close, and afterwards it tries to open and goes to some steady state, and afterwards again based on the following character the vocal tract shape will be differed. So, all these, the dynamics, all these changes in the vocal tract shape you want to capture with the appropriate mechanism, so that you can able to clearly discriminate the different sounds, right. So, for that if you use the only capsule coefficients, so each set of capsule coefficients of a frame, they will give you only the local information, like a discrete information at that particular instant what is the spectral envelope, right. And if you want to have the influence or like the influence of the previous frames on it, because the present frame is nothing but it is a follow up, is a continuation of the previous frames, and similarly the present frame influences the following frames also, because it is a continuum, it is in the continuous signal. So, therefore, So, if you want to properly analyze the speech sounds or a speaker characteristics whatever, it is better to have, instead of having capsule coefficients of a frames in a discrete manner, along with that if you can able to capture, right, the temporal information, or you can say that the temporal correlations of the capsule coefficients also along with the frame level. So, that we are performing here by taking the temporal capsule derivative. That means, if you take a capsule coefficients of a frame and then if you take a temporal capsule derivative, so it means that for doing that we will take adjacent frames, and by using this expression you can able to compute the derivative of a capsule coefficients of a particular frame. For doing that we will take 3 frames preceding to that and 3 frames following that. You see that here we are taking a summation where k varies from minus n to plus n, and this n will be of size usually n equals to 3 or 5 or something like that. So, therefore, here that means for estimating the derivative of a particular frame, capsule frame, we are considering the knowledge of the previous 3 frames or the previous 5 frames as well as the following 5 frames. So, with all of them together we are estimating the capsule derivative, and so that way you can able to capsule derivative. Usually for capsule coefficients, the number of capsule coefficients are q, it is nothing but 1.5 times of p, and if you want to consider the first order derivative, like they are known to be like a delta ci, it is nothing but first order derivative. So, this gives you another q coefficients, that means for every frame of this delta you need to take about like a previous 3 or previous 5 frames and following 5 frames. That means total around 7 frames including its own, right. If it is a 3, if it is a 5 means total 11 frames you are considering, and with all that knowledge together we will try to estimate the derivative of this one. So, the derivative means what it will do, it just tries to see the dynamics, that means from one frame to other frame what are the difference. So, those dynamics will be captured, because the first order derivative, if you look at here, it is nothing but taking a successive difference. So, taking a successive difference between one frame, here we considered that we will try to see the influence of a frame from the previous 3 frames or previous 5 frames to following 3 or following 5 frames. So, that way you can able to estimate the delta of ci, delta of c of n. It is nothing but the first order derivative of the capsule coefficients, that for every frame we have set of capsule coefficients, right, and if you assume all these capsule coefficients in the form of a vector, it means we have a feature vector, capsule feature vector corresponds to every frame, right. And now in addition to that, if you want to see like the temporal correlations also to capture that, or the temporal dynamics also if you want to capture that, then you can use the first order derivative, right. And if you want to capture further, right, you can also use the second order derivative also. Second order derivative means we will get a first order derivative capsule coefficients. On these first order capsule derivative coefficients, again if you apply one more derivative, like similar to the way we have performed here, like here we performed on the normal ci, right, capsule coefficients, we will get a first order derivative. So, now we have a set of first order derivatives, right. So, on this first order derivatives, again if you apply the same process, you will get a second order derivatives and all. Again the second order differential derivative coefficients, you will get again a set of q you will get. So, that depends upon here, if you use a normal just simple capsule coefficients, so the feature vector size will be q, right, it is nothing but 1.5 times of the order p. Suppose if p equals to 10, then if you use simple capsule coefficient, the feature vector size will be 15, and suppose if you consider the first order derivative, then it becomes 30, and if you consider the second order derivative also, it becomes 45. That way the size of the feature vector varies that depending upon whether you are considering the static characteristics of a vocal tract using just simple capsule coefficients, or whether you are using the first order derivative, or you are considering first and second order together. It is nothing but concatenation of these temporal dynamics or the temporal derivative of the speech signal and all, like first order, second order and so on. So, this way you can able to like add the temporal capsule derivative to the normal capsule coefficient, so that it contains both the static characteristics or the local characteristics, and as well it also contains the like the characteristics from the adjacent frames, or you can say that how the spectral envelope is changing with respect to the previous frame or with respect to the 2 frames before, like with respect to the frames that are there in future also, right. So, this way using these 8 steps you can able to derive the linear prediction capsule coefficients, and now after this whatever the feature vectors that we derive from the speech signal, so they can be used for discriminating for various applications, like in case of speech recognition I mentioned that it can able to discriminate the phones or discriminate the basic sounds, right. And whereas in case of speaker recognition, speaker verification, so the goal is that not to discriminate the sounds, it has to discriminate the speaker, like who has spoken the particular speech utterance. And likewise languages, in case of language we do not bother about who has spoken that and what is that. So, it is basically that the speech corresponds to which language it is, right. So, that way you can able to like carry out various speech tasks, and for doing that we use appropriate machine learning algorithm or a classification techniques or like any of the machine learning algorithms, and where these features, these capsule coefficients can be used as a features as a input features for the classification system and all. Yeah, the similar way so far we discussed about a capsule mandal. So, there are other features also you can able to derive. For example, if you want to represent the speech signal in terms of the spectral coefficient, simple spectral coefficients. So, for that what we do? We know that again the speech signal you cannot perform the spectrum analysis for the whole speech signal. So, we will try to the few steps, the first initial steps are same, like either for deriving the LPCCs or normal spectral coefficients also. It means first of all you need to pre-emphasize the speech, and afterwards you need to divide the speech into frames, then you apply a window. Then after that if you want to go with the LP analysis, you perform the autocorrelation analysis and use the autocorrelation coefficients for deriving the LPCs and so on. And suppose if you want to do with the normal spectral coefficients, then what you need to do, you apply a frame, you divide into frame and windowed, and then afterward the windowed frames you apply FFT on that, you apply the FFT on that, then you will get a spectral coefficients, you will get a spectrum, like you will get a spectrum something like this, right. This is the spectrum, and now you need to derive the coefficients from this spectrum, because when you perform the FFT you will get the, depending upon the FFT size, whether suppose that you are performing FFT with a 1024 points, you will get outcome of 1024 points, right. Out of this 1024 you can able to see that because of the symmetry, only if you choose the 512 points, that is good enough. So, that means you have total 512 values are there. So, from the 512 values you can able to see this is the way it is, and then those 512 values represents the frequencies from 0 to either 4 kilohertz or like 8 kilohertz, that depending upon the sampling frequency, right. And then we know that in a speech the speech signal where with respect to our auditory system and as well even the production also, you can able to see that the low frequencies are dominant, as we have seen when you look at the spectral envelope also, the low frequencies are very dominant. And from auditory perspective also, if you analyze, the low frequencies are very sensitive, or very like you can say that very sensitive. Our ear is also very sensitive to the low frequencies. It means that at the low frequency side our ear can able to discriminate the frequencies very effectively. It means, what I mean to say is that, suppose for example at a low frequency side you can able to discriminate the frequencies at the order of, for example, 10 Hz. It means you can able to discriminate, for example, 200 Hz and 210 Hz. That means when you listen to the like a tone of 200 Hz and 220 Hz, our ear can able to perceive the change. That means there is a change, that means you can able to see a clear discrimination or clear change if you perceive a sinusoidal of 200 and perceive a sinusoidal of 220. Whereas at a high frequency side, if we have a sinusoidal of 4000 and if you have a sinusoidal of like a 3900 like 3980 for example, that means there is a 20 Hz difference. Our ear cannot make out, our ear cannot distinguish those two, discriminate those two sinusoidals or those two tones at all. So, what I mean to say is that at low frequency our ear is very sensitive and it can able to discriminate the frequencies very effectively, whereas at high frequency side it is not that sensitive. So, at high frequency side you can able to perceive the change from 4000 to, like for example 3500, you can able to perceive the change, but you cannot perceive the change from 4000 to 3900 or 3900 to 3800, you cannot perceive the change. Whereas at a low frequency side you can able to perceive the change almost like at the intervals of 10 hertz or 20 hertz. So, that is what mean by sensitivity of ear for at a low frequency side and high frequency side. And well, ultimately since our objective of this speech transmission or speech is for end user is the human being, as our human auditory system is like the variable sensitivity across the various frequencies. At low frequencies it is a higher sensitive and high frequency it is a lower sensitive. So, therefore, when you are deriving the features from this spectrum also, you can give like you can able to extract like more coefficients like from the low frequency end compared to high frequency, because at high frequency it is not sensitive, right, and whereas low frequency it is very sensitive. So, therefore, in the 0 to 1 kilohertz you can able to say that you can able to represent this with the 16 coefficients, right, and whereas from 1 hertz to about 1 kilohertz to 5 kilohertz you can able to represent the whole this 4 kilohertz range with 16 coefficients, whereas here this only 1 kilohertz range you are represented by 16 coefficients, right. So, that way that depending upon the way you can able to do that. So, you can see here apply FFT, then afterwards you split the spectrum as per the requirement. Here in this case what I am doing is that, so 0 to 1 kilohertz is represented by 15 coefficients and 1 kilohertz to like 5 kilohertz is represented by another 15 coefficients, another 16 coefficients. So, here again the 16 coefficients I am just this 1 kilohertz range I am splitting that into 16 equal bins, and in each bin whatever the energy is there. So, that way I can able to represent the feature vector. Similarly, here also this 1 kilohertz to 5 kilohertz, the total 4 kilohertz range, this entire thing I will split it into 16 equal bins and then see that what is the energy that is there in the each of the bin, and that magnitude of the energy or that energy will be represented as my the feature, the value of that feature at that particular coefficient. So, that way you can able to derive the spectral coefficients directly from the spectrum of a speech signal of a particular frame. And similarly, and in the speech we have seen already, I have mentioned our auditory system where it is a non-linear. It means that all frequencies are not sensitive in a equal manner, right. So, we know that at a different frequency ranges our sensitivity will be different. So, in particular at low frequencies the sensitivity will be more, and as you move on to high frequencies the sensitivity will be less. So, therefore, there is a very important thing known to be Mel scale, that means the variation of the frequency ranges that is offered by our ear will be non-linear manner. So, therefore, in the Mel scale the way we do is that you can see suppose if you want to represent the total frequency the total spectrum with the 32 coefficients. So, then what we are doing here is that 0 to 1 kilohertz is represented by 16 coefficients and 1 to 2 is represented by 8 coefficients, and 2 to 5 this 3 kilohertz is represented by another 8 coefficients. So, that way in case of Mel frequency spectral coefficients means the way we do is that you apply you take a speech frame, windowed speech frame, then you apply a Fourier transform, you will get the spectrum, and now when you are extracting the feature vectors you apply a Mel scale on that, you superimpose the Mel scale on that. So, when you apply a Mel scale we know that here like 0 to 1 kilohertz is very important, and afterwards 1 to 2 kilohertz here also the ear is sensitive, right, but here as you go on the ear is not much sensitive. So, therefore, you can able to the 32 coefficients you can able to spread this way. 0 to 1 kilohertz is represented by 16 coefficients and 1 to 2 is represented by 8 coefficients and 2 to 5 is represented by another 8 coefficients, right. So, that way in a non-uniform way you can able to represent. So, this is a Mel frequency spectral coefficients, right. That means here the outcome of these will be derived directly from the spectrum, right. The spectral energies whatever is there in the different bins. So, they form the spectral vector, and suppose we want the capsule vector compared to the spectral one. So, the way we need to perform will be the same, like you have a spectrum, take a log spectrum of this and impose the MEL scale on that, and then afterwards you take IFT, that means inverse Fourier transform, then the resultant signal will be like the MEL capsule coefficients or a MEL capsule signal and all. So, that way you can able to derive the coefficients, right, the feature vectors from a speech signal as per the requirement and all, right. So, if you want to have the spectral coefficients, then directly from a spectral domain you can choose the depending upon the your requirement, you can choose it, like the ones what we have seen in case of filter bank. If you try to recollect in the filter bank analysis, so first initially we use the uniform filter bank, that means entire spectrum or entire frequency range is divided with equal bandwidths, right, and then we will observe the energies, and that becomes the feature vector for performing various speech tasks, right. This is known to be uniform filter bank. So, the other way is that actually like non-uniform filter bank, where we have seen the different types of non-uniform filter bank, like octave spacing, 1/3 octave spacing, right, and so we also seen that the non-uniform filter bank using critical band characteristics, right. So, we have seen similar to that here also almost the same concepts, but here the only thing is that we are not using filter bank, here we are using FFT, right. With the FFT you can able to get the spectrum, right, and then from the spectrum by applying different ways, like based on our auditory characteristic. So, the way the response of the ear for various frequencies. So, by knowing that we can able to handle, we can able to like split the spectrum accordingly, and we will give we will provide the number of capsule coefficients according to the desired requirement and all. So, that way the spectral coefficients you can able to derive, and then along then similar way along with the as you suppose for example in the capsule coefficients, we know that because this is a spectral coefficients where it involves, where the coefficients whatever you derive, it's a speech spectral coefficients. It means that the spectral information whatever is provided by these feature vectors, so they reflects both the excitation component as well as the vocal tract component also. They are mixed, right. Sometimes by mixing the vocal tract and the excitation component, like some crucial information will be not lost, you cannot observe from that, because they are mixed, because they are multiplicative in a spectral domain. So, therefore, sometimes at some places whatever the discriminative characteristic of vocal tract system alone, so that may be spoiled with this multiplication, effect of multiplication, right. Similarly, the excitation characteristics also sometimes that may give you the very discriminative characteristic, and that excitation characteristics also will be spoiled by the multiplication of this excitation characteristic spectrum with the vocal tract spectrum and all. So, therefore, if you want to observe the spectral components of the individual components of these components separately, that means the vocal tract component separately and the excitation component separately, right. If you want to perform that, then we need to go for a capsule domain, right. So, that is the reason that we have a MEL frequency spectral coefficients, where the spectral information of both the vocal tract and excitation together is observed over here. And if you want to perform, or if you want to look at the this one, the vocal tract characteristics alone, right, vocal tract characteristics alone, because as you know that the vocal tract shape will be different for different sounds most of the cases, right, along with the excitation also. So, therefore, if you want to capture the vocal tract characteristics alone for discriminating the sounds, right. So, in that case we can apply the capsule analysis. So, by applying the capsule analysis and using the capsule coefficients, that means very near, or like the first few capsule coefficients, like first few means the like 1.5 times the p or approximate capsule coefficient, if you choose it, they basically represent the vocal tract shape, and the influence of excitation will be very less on that. So, that with only excitation, with only the vocal tract shape information can be used, can be exploited for discriminating the either sounds, or discriminating the speakers, or discriminating the the other specific task, whether it may be emotion or whether it may be the other task like language identification and so on. So, that is the reason that we have these MEL capsule coefficients and MEL frequency capsule coefficients. In addition to these, likewise you can able to derive even the other features like PLP features is known to be like perceptually linear prediction coefficients. It means that so far we discussed about linear prediction analysis, but the perceptually linear prediction analysis means, and after you derive the linear prediction coefficients, then based on our auditory characteristics or perception characteristics, if you can able to apply weights, different weights, right, on these linear prediction coefficients based on our perception or based on our auditory characteristics or based on our perception. So, then they are known to be like a perceptual linear prediction coefficients, known to be PLP, like, and again if you perform a capsule on that, then it becomes a perceptual linear prediction capsule coefficients. So, there are like so that way you can able to derive, and you have other coefficients like a Rasta PLP, like we have a different types of features you can able to derive, but for all of them the basic the input is a speech signal, and then you can able to derive by performing different operations. Either you can able to derive the spectral coefficients or capsule coefficients or perceptually weighted or perceptually linear prediction coefficients, all of them you can able to derive from that, right. So, with this we stop this lecture, and we will continue the this one in the next class. It is the LP analysis further with some important illustrations in the next class. So, we will stop here. Okay, thank you.